Consider this counting question. Given a set of states Q0, Q1 and so on, and an input alphabet say containing 0, 1, how many different DFAs are possible? When we construct a deterministic finite automaton, which means if you look at the underlying transition function, it is from Q cross sigma to Q. So each DFA has an equivalent transition function. So number of different DFAs, counting this is equivalent to counting number of different transition functions. And we know how many different functions are possible from a domain of size m to a codomain of size n. So you just count what is the cardinality of the domain, what is the cardinality of codomain. With that we can count the number of functions which map Q cross sigma to Q. And little more work on that will answer this question. Okay. So just look at, let's look at a couple of examples, then we will focus on this generalized question. Let's assume Q has got just Q0 and sigma has got say 0. Okay. Then on Q0 you have to read this symbol, and on reading you have to stay in the same state because there are no other states in this. And in one automaton you say you accept, meaning Q0 itself is a start state and end state or the final state, and in this there is no final state at all. What is the language accepted by this automaton? Suppose this is M1. Language accepted by this automaton is empty set. It does not accept anything. And language accepted by this automaton is 0 star. It accepts epsilon and 0 once, twice and so on. Now if you count the function, so Q cross sigma to Q. Q cross sigma is Q is Q0 and sigma is 0 mapping to Q0. So how many functions are possible from a domain of size 1 to a codomain of size 1? In general, number of functions from A to B. So number of functions from A to B is cardinality of B to the power cardinality of A. Correct? That's precisely what we did when we looked at the module on function, right? Which means this tells you that only one function is possible. But we are not just interested in this map. On top of that, we wish to add the start state as well as the final state. So now you get so many functions, and in each of them you look at the possibilities for start state and the terminal state. And now since only one state is there, it has to be the start state. Final state can be there or it need not be there. For example, in this case it is not there and it is still a finite automata. It is still a deterministic finite automata. Only thing is it accepts nothing or an empty set. So there are possible values for the final state. which means in this start state is only 1 and final state there are two possibilities. One is empty set, another one is set containing Q naught. So in this case it is set containing Q naught. When I say empty set, no final state. Okay. So that tells you that for this specification we have two DFAs. Okay. So now let's look at a couple of more examples and then let's generalize. So let's look at our second example where Q has got Q naught Q1 and sigma is just 0. So in this case, the transition function tells you that Q cross sigma to Q, which means the pairs are Q0 comma 0 and Q1 comma 0, and it's going to Q. On the other side it is just Q0, which means these two are mapping to this, so only one function is possible. Now on top of this, so which means only one function is possible, you have got Q0 comma 0 is this, and you also have something called Q1 and Q1 comma 0 is mapping to Q0. Okay. So this is one function, Q0 comma 0, Q1 comma 1, and they both are mapping to Q1. The other function is Q0 comma 0, Q0 comma 0 is mapping to Q0, Q1 comma 0 is mapping to Q1, and so this is function number 1, function number 2, function number 3, function number 4 is Q0 comma 0 is mapping to Q1 and Q1 comma 0 is mapping to Q0. Fine, so this gives you 1, this gives you another 1, so like that 4 functions are possible correctly, yeah, because Q has got 2 elements and sigma has got just 1 element, and that is mapping to Q0 comma Q1. So cardinality of B to the power cardinality of A, cardinality of B is 2 and 2 into 1 is 1, so cardinality of this is 2, so there are 4 functions possible. So Q0 comma 0, Q1 comma 0 mapping to Q0 is 1, this is second function, third function and fourth function. Now in each of this one can add the start state and appropriate final states. So let's focus on this function and see how many finite automatons, deterministic finite automatons, one can get out of this function. Similarly out of this function. So like that for each of them, let's do the counting. So let's look at the first function, which says q0 comma 0 and q1 comma 0 both are mapping to q0. So it's like this. q0 comma 0 and q1 comma 0 both are mapping to this. Now this is all the function is giving us. Like this we have 4 different functions. Now I need to convert this into a DFA. To do that, we need to add start and final states. Now this can be a final state or this can be a final state. So 2 possibilities are there. Let's assume q0 is a final state. Then we get this automaton. And if you assume q1 is your final state, then we get this automaton. Okay. Now this is by adding initial states. Now in this case, q0 is the start state, and in this case q1 is your start state. So now just one function giving us 2 more deterministic finite automatons. Now we have to add final states. Now possible final states are none of them are final states, empty, or q0 is the final state, or q1 is the final state, or both are final states. What is this? This is precisely 2 power cardinality of q or power set of q. So the cardinality of power set of q, which means keeping q0 as the start state, I get this automaton, or with q0 as the start state, the first one says q0 itself is your final state, so we get this. Or with q0 as the start state, this says q1 is our final state, we get this. Or with q0 as the start state, this says both are final states, we get this. And all are different. This automaton is different from this, is different from this, and different from this. What is that we have achieved? By taking this function, by keeping q0 as the start state, we have identified 4 different deterministic finite automata. Similarly, with q1, we will have 4 possibilities: empty state, and this being the final state, then this being the final state, and both. So for function number 1, we get q0 with q0 as the start state. Let me write with Q0 as start, we get 4 DFAs. And with Q1 as start, we get another 4 DFAs, which means we get 8 DFAs out of this. And argument is symmetric, meaning with F2 we get another 8 DFAs. With function F3 we get another 8. With function F4 another 8, which means we get 32 DFAs out of this. So given Q0, Q1 and alphabet being just 0, there are 32 deterministic finite automatons. Okay, now in general, how do we count? And can this case, is there a learning which one can generalize? So now we see that total number of functions for this example, it is 4. How did we arrive at that number? Is 2 square into possible values for this are 2 and possible values for the final states are again 2 square. So we therefore get 32. So this one is Q cross sigma to Q. Correctly, yeah? That gives you the number of functions. Then this gives you number of possibilities for start state. This gives you the number of possibilities for final states. Okay, that tells you that there are 32 deterministic finite automatons for this example.